Welcome back. In this chapter, we will discuss the steps that we have to take if we want to run the ATmega without the Arduino board. The Arduino board is a nice development board for prototyping, since all pins are exposed and can be connected to all the peripheries that a project requires. However, it is also quite large, especially when compared to the size of the ATmega chip. Obviously, there are smaller Arduino boards out there, down to the Arduino Mini Pro. However, instead of buying a new board, which again has items such as the power LED, etc., which are maybe not required, the ATmega 328P can be removed from the board. But what does it need to run solo? That will be the topic of this chapter. First, we have a look at the Arduino board and the minimum requirements. Then, step by step, we replicate those requirements. That starts with duplicating the power supply, the reset, and the clock till the end, when we have something like this. So let's get started. This is an Arduino board. The Arduino 2009 is quite old and has been replaced by the Arduino Uno. However, the principles remain the same. Let's have a look at the different functionalities that this board provides. The first is the power supply. While this board usually draws power from the USB port, for instance, doing programming, it can also run from a battery, for example. This plug point is designed to accept DC in the range from 7 to 20 volt. Usually, there is a voltage converter like the 7805 converting this voltage into the acceptable 5 volt that we need. The 7805 on this board might be either this chip or this chip. The output current of this 7805 can go up to 1.5 amperes. But the component suffers from heavy heat losses, and therefore a heatsink is recommended for projects that consume more current at 5 volt. For example, if the input voltage is 12 volt and you are consuming 1 ampere, which is quite a lot for a project, then 12 minus 5 volt into 1 ampere equals 7 watts. These 7 watts will be dissipated as heat. 7 watts don't sound much, but I'm sure that this board is not going to survive that, and you do not want to touch it. Or another example, let's say you connect a 9 volt block battery to this plug point. If you draw 200 milliampere of current, which is not unrealistic depending on the project, still 4 volt into 0.2 ampere, which is 0.8 watts, are dissipated as heat. Every heat generation shortens the battery life. Hence, if the project depends on a battery, choose the battery and its voltage carefully. We will talk more about batteries in a little bit. Then we have the USB port and the programmer. In old Arduinos, this programmer was the FTDI-232, and it is still in use as of today, as we will see at the end of this chapter. The FTDI converts the USB signals into the UART signals and generate the reset before programming so that the bootloader is executed. And we have the pin headers. All pins which are not used internally by the board are exposed, allowing the developer to attach periphery to those conveniently. To show the current state of the board, there are LEDs for the UART, power, and the onboard LED that we already used in the exercises, including the required resistors. Then there is a reset button and the crystal oscillating at 16 MHz in the silver casing. These two capacitors of 22 picofarad are part of that oscillator. And those are the main parts. Once the project is to be deployed, the developer might not need the headers or the LEDs anymore. Removing them reduces cost and size of the system. Okay, so what are the requirements to run the ATmega in the first place? First and most obvious, we need some power and a source. Since the reset and the clock generator is also on the Arduino board, we have to find alternatives for those as well. And once the ATmega has been extracted from the board, can it still be programmed to apply last-minute changes, for instance? This chapter handles all requirements one by one. First, the power supply. The datasheet reveals the maximum operating voltage of 6 volt. However, keep in mind that these are the absolute maximum values. Any crossing of those maxima might damage the chip immediately and permanently. What power supplies fall into those specifications? Here are some. The indicated battery voltages are the nominal voltages. Obviously, if the battery is drained and depending on the current that is drawn from the battery, the voltage decreases. A fresh AA battery might have more than 1.5 volt, and 4 of them in series will cross the maximum voltage of 6 volt. On the other hand, the voltage of the 1.5 volt battery might go down to 0.7 or something similar when a high current is drawn from it. It depends on the internal resistance of the battery under consideration. The higher the resistance, the earlier the voltage drops when the current is drawn. Lithium-ion batteries have a very low internal resistance and hence can deliver a high current at a high voltage. That is, for instance, evident from the recharging of camera flashes. In the earlier days, cameras worked on AA batteries, and some of us might still know the high-pitched sound it makes when the capacitors of the flash are charged. It took a minute or so to fully charge those capacitors. Nowadays, flashes are smaller, but the principles are still the same. The charging of the capacitors of a flash is done within seconds. And that brings me to a word of caution if you work with lithium cells. If there is a short circuit, then a high current can be delivered due to the rapid discharge. This generates heat within the battery, which cannot be dissipated fast enough. The battery becomes a so-called thermal runaway, eventually turning adjacent cells also into thermal runaways. Then the cells rupture and release the content into its surroundings, posing a danger to everybody and everything. Once burning, the fire cannot be extinguished by normal methods. Therefore, if you consider a project containing lithium or lithium-ion batteries, please be careful. Do not shorten them, do not overcharge them, undercharge them, and make sure that they are of high quality. Also, remember to dispose them properly and not in a normal trash, as they can again catch fire in the trash, which usually contains plastics which burn easily. In this chapter, we would like to connect the power supply directly to the ATmega. That means that batteries with higher voltages are not considered for the moment. One goal of this chapter is to prolong the battery life. Therefore, we want to avoid using a voltage regulator like the 7805, which inherently causes losses in form of heat, as mentioned earlier. Also, when selecting the voltage that, for instance, the battery can supply, we have to consider the clock frequency that those voltages support. The diagram shows that the full 20 MHz is only available when VCC is 4.5 volt or higher. From 4.5 volt, the frequency decreases continuously. Therefore, if the power supply is, let's say, two AA batteries supplying 3 volt, we cannot run the ATmega 328P at 16 MHz, but around 12 MHz. It might work at 16 MHz, however, there is no guarantee for a smooth operation since it is outside of the specifications. Let's establish connection to supply the power. We have a battery on the left and connect the positive terminal to VCC and AVRCC, which needs to be between plus minus 0.3 volt of VCC. The negative terminal of the battery is connected to ground. If the power supply fluctuates and the project utilizes the ADC, the voltage to the AVRCC should be filtered through an inductor of 10 microhenry and a capacitor of 100 nanofarad, posing as a low-pass filter. However, in case the power supply is stable or the sample data by the ADC does not need to be accurate and utilizes, for instance, only 8 bits, then directly connecting AVRCC to VCC might suffice. The second step is the reset. The ATmega reset pin is an active low pin, which means that the reset is issued if that pin is driven low and connected to ground. To make sure that the ATmega does not reset, connect this pin through a 10 kilo ohm resistor to VCC. To reset the ATmega, the reset pin can be temporarily connected to ground or by a button like this. That was the easy part of the requirement replication. What about the external clock? How we can replicate this crystal as easy as possible? Many embedded systems are deployed in remote areas and hence depend on batteries. Can we extend the life of the battery by reducing the clock without compromising on the computation capabilities? Usually not. However, in many systems, a slower clock is not a problem as many do not perform heavy computations. With the reset and the easier version of the power supply, adding an oscillator to the design seems to be relatively complex. Once we remove the ATmega from the Arduino board, this functionality is not available anymore and needs to be replicated, since without a clock, no data is going to move in the ATmega. What are the options? Fortunately, the datasheet reveals them. We have the low power crystal oscillator, full swing oscillator, etc. It seems that the internal oscillators are the most interesting ones, and there are even 2 of them. The calibrated internal and the 128 kHz internal RC oscillators. The internal calibrated oscillator gives a frequency of about 8 MHz, which is half of what we currently have, while the 128 kHz internal oscillator swings well at 128 kHz. If we use one of those oscillators for clock generation, we can run the ATmega without any additional components apart from the power and reset that we already have. Let's check how the bits can be configured. The clock is quite important for a chip, since without it, it cannot do anything, not even programming, nor reading a configuration register. That is why the clock select bits are stored in the fuse, and that too in the low fuse byte as shown here. And here lies the first thing that complicates the entire topic of configuring fuses. A0 means that the fuse is programmed, while the unprogrammed fuse has a value of 1. That is quite counterintuitive. We try to make it easier once we are more advanced in the topic a little bit later. Let's see what those settings in the low fuse mean. The most significant bit is the CK-diff8. We see that by default the fuse is programmed and hence the setting is active. If active, the system clock is automatically divided by 8. Let's say the ATmega is in the Arduino running at 16 MHz. Setting that fuse will reduce its clock to 2 MHz. Since the fuse is non-volatile memory, the setting is active after every power cycle and reset. The implementation of that fuse bit is quite simple. There is a register which allows the software developer to dynamically adapt the clock speed to different scenarios while the user program is executed. If CK-diff8 is programmed, the clock PS bits will reset to the value of 0011 in binary format. If clock diff8 is unprogrammed, those bits reset back to all bits cleared and a clock division factor of 1. CK-diff8 can also be used if the crystal frequency of the oscillator exceeds device specifications for a specific VCC, and it is programmed, that means activated, for new ATmegas to allow them to be clocked for all kind of VCC levels. The next bit is CK-out. If that bit is programmed, the same system clock is applied to pin PB0. It allows the ATmega to clock other components and even other ATmegas connecting the XTEL1 pin to the clock out pin. The default is that this pin is not used for the clock output, hence the CK-out bit is unprogrammed when a new ATmega is bought. What else do we have? The SUT bit, which there are 2 of them. They define the startup time. What the startup time is depends on the selected clock source. Here is the table for the internal oscillators. Although the internal oscillator should be up and running almost immediately, the SUT setting can be used to give the rest of the circuit enough time to get up and stabilize before the ATmega is taken out of the reset after powering up the entire circuit. It does not make sense trying to start executing the user program if the attached circuitry is not yet alive. Unless there is a need in the project to start quickly from a power on reset, use the longest time available. If the shortest time is necessary, it needs to be established first how long each peripheral subsystem needs to stabilize when powered up. After selecting a new setting, the low fuse needs to be programmed. Unfortunately, it cannot be achieved while executing a user program or the bootloader. Fuses cannot be programmed by UART. They need to be written to using another protocol that can also be utilized not only to program the fuses, but to program the EEPROM and the flash. For that, many Arduino boards have those 6 pins labeled ICSP. ICSP stands for In-Circuit Serial Programming and is sometimes also called ISP for In-System Programming. It is a way to reprogram the chip while it is integrated in the system. Hence, it does not have to be removed or plugged into a dedicated programmer. The meaning of the pins are 5V for VCC, ground, clock, MISO and MOSI. Do you remember what protocol that is? It is the Serial Peripheral Protocol, or also called SPI, that we had some chapters ago. So what can I do with those pins? There are some neat programmers available which can be plugged into the ICSP header and into the USB port of the computer. They also come in a fancy casing with switches to control VCC. Some chips have a maximum voltage rating of, for instance, 3.3V and not 5V. They all come in various shapes and price ranges, all doing the same thing. Programming the chip through the SPI. Before buying something to set the fuses for this course, what are the alternatives? The left picture already gives a hint. It is an Arduino shield that fits exactly into the pin headers of an Arduino. So can we use an Arduino to program an ATmega, since we know it also has the periphery for SPI? And it turns out that we can. In fact, using the Arduino IDE that we ditched many course hours ago allows us to conveniently program an Arduino to function as an ISP. So let's try that out. First, the connections. We connect pin 13, which is the SPI clock of the programmer, to pin 13 of the target. In fact, we connect ports 12 and 11 that are MISO to MISO and MOSI to MOSI. In this diagram, I connected pin 5 of the programmer to the reset pin of the target and established the VCC and ground wires in pink and gray respectively. In addition, the programmer sports a 10 microfarad capacitor between its own reset and ground pin. The purpose of that capacitor is to prevent the programming Arduino from resetting when the serial port is opened and AVRDude is executed to send the data to the target. If the programmer board resets, then the programming fails. It is just one way to prevent the programmer to reset, but this one is the simplest. Please do not forget to remove the capacitor if you want to upload the Arduino ISP sketch into the programmer. Here are the connections once again for your reference. If you would like to recreate the connections, I am attaching the last 2 slides to the resources folder of this lecture. Connections 13 to 11 are directly connected, while 10 or 5, for instance, are connected to the reset pin of the target. This pin is configurable, and old Arduinos do not work if pin 10 is used. Hence, the Arduino ISP sketch allows us to define another pin, which can be anything apart from TX and RX. Then, the power supply of 5V and the ground are connected to the same pins of the programmer and the target. If there is a user program on the target that makes the LED blink, it should do so by now since the target board is powered. If you do not have 2 Arduinos or different Arduinos, please have a look at the attached link for various constellations. Do not forget to connect the capacitor to the reset pin for the programmer to prevent it from being reset when the UART port is opened. Also note that the electrolytic capacitors are polarized, meaning the two pins have to be connected to the proper terminals. The white band on this one shown here indicates that this pin needs to be connected to ground. Have a look at yours. You can try to run it without the capacitor and it might work. Personally, I have mixed experiences. Some configurations can be easily configured in the Arduino ISP source code once opened in the Arduino IDE. To load the sketch, go to Files, then Examples, and search there for Arduino ISP. First, the pins for the reset can be set. The default is 10, but it might not work for your Arduino ISP. As alternative, I put in the 5th pin and had success. In addition, pins LED HB shows a heartbeat indicating the state of the ISP. If an error occurred, an LED attached to pin 8 at the moment will glow. And if there is communication going on between the programmer and the target, the LED in pin 7 will show that traffic. If you use the ICSP header, you can comment the #define use old wiring. And another important setting is the SPI clock. In the lecture about SPI, we figured out that the SPI clock is derived from the system clock. And in this chapter we saw that we can set the clock source of that system clock in the low fuse setting. What if we mess it up and set a clock in the target that is very slow? That means the current clock of the programmer set to 1 million divided by 6 will be too high and too fast. The slow target will not communicate properly, and a reviving by rewriting the low fuse will fail. The setting shown here allows the software developer to set the SPI clock in the programmer to a lower value than the standard one. For instance, if the 128 kHz internal oscillator is programmed, you will regain access to the target if the SPI clock is set to this frequency in Hertz divided by 6. 6 because the SPI clock needs to be larger than 2 clock cycles, and a SPI clock period consists of a low period and a high period. So it is safe to assume that 6 system clock cycles are required for 1 clock period of the SPI connection. If programming fails, try out the capacitor between the reset and the ground, another pin to issue the reset to the target, or a lower SPI clock frequency. Okay, once the Arduino ISP sketch has been uploaded to the programmer and this programmer has been connected to the target, we can try it out using AVRDude. Instead of using Arduino as programmer in the configuration, we use AVR-ISP. By default, the baud rate is 19,200. Set the port and configuration file, which is the same from the make files in the exercises, and try it out. If everything was done correctly, we get a reply from the target. As you can see, I did not include any U parameter, which means that neither memory is written to nor read from. However, there is a tiny difference in the output compared to the one of the exercises. Earlier, the fuses were all set to 0, but now they have values. The extended fuse is set to FD, the high fuse to DA, and the low fuse that is of interest to us at the moment to FF in hexadecimal format. If you do not get this output, make sure the connections are correct and the capacitor is inserted. Do not, and I repeat, do not use the minus capital F parameter for AVRDude. This parameter skips the signature check. Simple reason: if the data transmission cannot even read out the signature of the target, then the same data transmission will not carry the correct fuse settings either, and since they are so important, we should not risk that. Let's examine what the values FF for the low fuse means, so that we can establish the new value for the low fuse. Okay, first do note again that A0 means a programmed, while A1 stands for a unprogrammed fuse. A low fuse setting of FF in hexadecimal format means that all bits are programmed from the CKdiff 8-bit to clock select 0. That means that clock diff 8 and clock out are deactivated, since unprogrammed means deactivated, although it is logic 1. Clock select 3 to clock select 1 are currently all unprogrammed, indicating that the clock source is currently a low power crystal oscillator operating between 8 and 16 MHz. And that is the silver oscillator on the board. Clock select 0, SUT 0 and 1 are also unprogrammed, which means that the startup time and reset delay are maximized. Now the question is, what are the fuse bits to be set to if both clock diff 8 and clock out should remain inactive? The startup time shall still be maximized, but the clock should be the internal 8 MHz oscillator. I'm going to interrupt the lecture here to give you time to think about the solution. We will continue after the countdown. Okay, clock diff 8 and clock out remain unprogrammed and hence 1. SUT1 and SUT0 need to be set to the longest startup time, which means that SUT1 is unprogrammed and SUT0 is programmed. And lastly, from the clock select bits, only the first bit is to be unprogrammed, while all other bits are programmed. Hence, the value of that low fuse needs to be E and 2 in hexadecimal format. The setting of the fuses can be quite counterintuitive. Therefore, there is an easier method which I highly recommend to avoid errors. In the end, we must leave no doubt that E2 is the right setting. A wrong setting can make it very hard to recover the ATmega. Imagine you set the fuse to some obscure setting. Now you have to guess the setup and try to create the right clock to bring it back to life to reprogram the ATmega to the intended setting. Especially the high fuse has the potential to brick the ATmega, so make sure you do not touch that one for the time being. Once the fuses carry the wrong setting, only a high voltage programmer can forcefully override that setting. But enough warning, just remember to be careful. Double and triple checking just takes a minute, Recovering a wrong setting might take hours or days for the next shipment of ATmegas to arrive. Therefore, some nice people came up with online fuse calculators. I will put the links into the resources folder. First, select your ATmega. We have the ATmega 328P. And then you can select the fuses. You can also start with the current setting, that is FF for the lower fuse, DA for the high fuse, and FD for the extended fuse. If you click apply, these settings are changing and you can see what they mean. For instance, currently the setting for the low fuse is no clock output, no division by 8, and the external crystal oscillator with a frequency higher than 8 MHz is active. The startup time is the maximum 65 milliseconds. Now we want the 8 MHz internal RC oscillator with a maximum startup time. So we select the internal RC oscillator but with 8 MHz and the maximum startup time is 65 milliseconds, and we leave the division of the clock unchecked and the clock output unchecked to deactivate these two options. And we see here the setting of the low fuse, and the new setting would be E2. So we did do the right calculations. This online fuse calculator even gives us the parameter line for AVRDude. The M parameter indicates that this part is not a file name but a manual value. It says program the low fuse with this value. Leave the other fuses untouched. So let's take this parameter and build our parameter list for AVRDude. And that is the complete parameter list for AVRDude to program the low fuse. Same settings as before with the AVR ISP and the U parameter copied from the online fuse calculator. It writes the new value and checks it again. If there's a mismatch between the value to be written and the verified value, AVRDude is going to ask you if the fuse value should be recovered. Do so, since we do not know if it really worked. Congratulations, you did it! Now the ATmega runs at 8 MHz. Even if you reinsert it into the Arduino board, it will still run at 8 MHz. Please remember that. I used to tag them with some paper to remind me about that clock setting, so I can use the right dfcpu parameter in the makefile. To develop the software in a project, I would recommend the following sequence. First, set the fuses to the values that you would like to have. That will eradicate bugs introduced when the frequency is changed later, and all the programming is tested with a new clock while keeping the ATmega in the Arduino development board. Therefore, the pin header allows an easy debugging and access to the pins. Then extract the ATmega or get a separate chip and upload your user program into it. Remember to set the fuses to the same values like the prototype. Integrate the prototype on the test board and recheck your test benches. If you like, you can program the fuses such that there is no bootloader executed and your program is locked and cannot be downloaded from the chip to protect your intellectual property. Only a complete chip erase will reset those lock fuse bits. And as a last step, enjoy your embedded system. But what if the ATmega has already been removed from the development board? Sometimes it is required to reprogram an ATmega that is already extracted or was never inserted in a development board in the first place. How to do that? Well, it has its normal pins as shown here. Instead of using ports 11 till 13, you have to connect wires to PP3, 4 and 5. The pin headers of the Arduino board are directly connected to those pins. Therefore, there are two options. Using the programmer on the Arduino board and connecting the pins 0, 1 and reset to the pins PD0, PD1 and reset respectively to program the ATmega through UART and a bootloader. Or alternatively, connect the SPI port of the Arduino ISP directly to the pins of the ATmega, which is the target. Remember to wire two grounds, VCC and the AVRDude pin of the target ATmega accordingly. And remember that pin 10 is configurable if you need another pin. Instead of utilizing the programmer of an Arduino board, they are also sold separately. It is called an FTDI232 and it looks like this. You might recognize the same chip sitting somewhere on your Arduino board. It also has the luxury to select the VCC of 5 or 3.3 volt via this jumper. There are 6 connectors opposite of the USB port, and they are connected as shown in this circuit diagram. The complicated thing is the reset, which needs to be pulled high by this 10 kilo ohm resistor and this decoupling capacitor. You may have success without this capacitor. Try a few times. And another interesting information. Remember the lecture in which we discovered that there are protocols which can mimic other protocols? We used UART to get a one-wire signal, which is not supported in the ATmega except by bit banging a pin, which is quite expensive in terms of computation resource requirements. And we saw that UART can look similar to SPI. So the question is, can the FTDI232 be used to bit bang an SPI signal so that it can be used as an ISP? Yes, it can, as you can see in this figure in which the FTDI is connected to the SPI port. I'm going to attach links to the resources folder explaining how to do that. Basically, it is in the configuration file that we keep using when invoking AVRDude. In it, there is a programmer called FT232R, which is the FT232R synchronous bit bang, which sounds exactly like what we need. The only thing is, we have to configure which pin has which meaning. All is explained in the linked websites. Please have a look. And that brings me to another question. Why should we use an external FTDI if there is already one on many of the Arduino boards? The stupid thing is that the pins of the FTDI are hardwired to RX and TX. However, have you ever wondered what the meaning of the solder pads are, the ones which are labeled X3? You can solder a 4-pin header to it and the reset, MOSI, SCK and MISO of the FTDI chip are exposed. Which means that you just need to connect those pins to the onboard pin header or alternatively to the ICSP header, and automatically you have built an ISP which is able to access the fuses. No second Arduino is required. And with that, I conclude the lecture, and I hope I gave you some interesting ideas. What did we do in this chapter? We extracted the ATmega from the Arduino development board and replicated everything that it needs to run. We also learned how to program the fuses and that we have to be careful in doing so. To help with the programming, online fuse calculators were introduced. And what is next? Apart from the smaller size, we see that we also benefit from a lower power consumption when the ATmega is extracted, since we do not have to power all the components that are not needed for the project. In the next chapter, we take it a step further, and I'll show you some tricks how to reduce the power consumption drastically. In addition, some programming guidelines are also given. Apart from that, let's extract the ATmega in the exercise for this chapter, since you will need it to do the experiments in the next chapter. Exciting times! After the exercises, I will see you again in the next chapter. Thanks for watching!